complex pedantic theorem.
Today we are going to learn about a very special topic in physics, the wave. Now this wave is not new dance sensation. No, it is a periodic something or other that, like when you throw a rock in a pond.
Hi, I'm Jeremy Clavens, and I'm sure you guys want to learn physics in an exciting way. Well, grab your goggles and strap on your oxygen tank, because in the next 2 hours, we're going to explore the concepts of heat, waves, Kepler's laws of planetary motion, and a whole lot of other good stuff.
Now we know that physics can be a rough ride at times. Well, we, the Standard Deviants, have scoured the nation for all the introductory materials you need to know, and then hired some creme de la creme physics professors to help us out. You can count on us to simplify this stuff to make it easy to learn, easy to remember, and just a little bit enjoyable. Believe it, it's our job.
As a licensed physicist, I lead a pretty full life. The fame, the money, the glory. But none of these things would be possible if I hadn't gone to class, read my textbooks, and listened to my professors. I suggest you do the same. Maybe you won't gain fame and fortune, but then again, maybe you will.
Sometimes it's easy to forget that this is a videotape. It's easy to trick yourself into thinking that this is some obscure program on a UHF station. But rest assured, this is a videotape. So,
once you get started, anytime you feel like slowing down,
speeding up,
pausing, or rewinding, and now we roll, feel free to do so.
On to more important matters. There are many equations in physics, but just for you, we put all the ones we talk about on the insert card that's included with this videotape. Also, since this is the Gravity-Packed World of Physics Part 2, we'll be building on the principles we learned in the Gravity-Packed World of Physics Part 1.
Once you've reviewed, we can get down to business, starting with
Part 1, Work and Energy.
Just like Starbucks and the Wayans brothers, energy is all around us. For example, we can be energized by eating energy bars, or we can have a tremendous loss of energy after running a marathon. But to understand energy, we've got to understand the concept of work. So, let's look at that now.
Section A, Work.
It's a common experience that the longer and harder we push an object along on a horizontal surface, the more tired we get. Work is the measure of the force applied times the distance moved, or the displacement. If either force or distance is zero, then no work has been done, and nothing has been accomplished.
So if this guy pushes his pet rock across the table and the rock goes nowhere, then no work has been done. But if he pushes just a little bit harder, the rock moves and work has been done because the object has been displaced.
That sound you hear? That's the sound of men. They're working on the chain. Gang. See, in life, work comes with a minimum wage, a lunch break, and if you're lucky, a health plan. Of course, in physics, work is all mathematical.
In physics terms, work can be described as the dot or scalar product of the vectors, force, and displacement. So work, or W, equals force, F, dot displacement, x. We learned how to compute the dot product from the gravity-packed world of physics, part 1, where vector A dot vector B equals the magnitude of A times the magnitude of B times the cosine of theta.
So if theta is the angle between the two vectors, force and displacement, then work, W, equals the dot product of F and x, which equals F times x times the cosine of theta. So from now on, this is the equation we'll use to find work. Remember, you can find this on your insert card.
Since force is measured in newtons and displacement in meters, the unit for work is the Newton meter. This is also called the joule, a capital J, so 1 Newton meter equals 1 joule.
You know, don't think that you can go into a jewelry store trying to exchange a Newton meter for a joule, though. The white-coated men will take you away. They'll throw away the key and you will be in a world of darkness. But you know, that's a story for another time, really. Let's do a problem now. Okay, problem.
Suppose Forrest has eaten way too many chocolates, so desperately trying not to eat anymore, he pushes the box away from himself. The box moves 0.3 meters. He pushes it with a force of 200 newtons at 45 degrees. What is the amount of work he did to move the box?
Okay, we know that work equals F times x times the cosine of theta. We have the force, 200 newtons, the displacement, 0.3 meters, and the angle between Forrest's arms and the bench, which is the direction of the motion, 45 degrees. Plugging all this into our equation, we get W equals 200 newtons times 0.3 meters times the cosine of 45 degrees, which equals 42.4 newton meters, or 42.4 joules.
So it takes 42.4 joules of work for Forrest to push that box of chocolates 3/10 of a meter.
Anyhow, all this work stuff, it's not easy. See, because when we got to move something upward, the work done is going against gravity. So to overcome this, we have to account for gravity somehow. We do this by exchanging the force in our equation with weight. That's it. That's how it's done.
Remember, weight is a vector that takes gravity into account. Since we're pushing in the opposite direction of gravity, the work done by us is the negative of the object's weight times the object's displacement, which in this case is the height that the object moves.
We learned about weight in part 1. Weight, little w, is mass times the acceleration due to gravity. Remember, the acceleration due to gravity equals negative 9.8 meters per second squared.
Since work equals the negative of weight times height, work against gravity equals the negative of negative mg times height. When we simplify, the negatives cancel out, and work against gravity equals mass times the acceleration due to gravity times height, or capital W equals mgh.
So to raise an object to a certain height, the work done is the object's mass times the acceleration due to gravity times the height raised. Now, when the object reaches a certain height, the work that can be done by the object is the change in the object's gravitational potential energy. Gravitational potential energy is represented by capital P, capital E. So, mgh equals delta PE. We can show you how this works with the help of those lovable mismatched cartoon brothers, Bumpkin Bill and Urban Tom.
In this week's episode, Bumpkin Bill goes to Urban Tom's co-op to help move in a safe. The only problem is Urban Tom lives on the top floor. Pulling that safe up is no easy trick, and once to the top, it has a lot of potential to do work if Bill lets go and it falls. This capacity to do work by falling is the safe's gravitational potential energy. But until it falls, no work is done by the safe. It's all done by Bill while Tom just looks on. So before Bill drops it, let's use our equations to find out how heavy that safe is.
W equals mgh is our formula for the work done on an object moving vertically in either direction.
Urban Tom's co-op is 16 meters high. If it takes 9,600 joules for Bumpkin Bill to raise the safe to the top of the building, how much does the safe weigh?
The question asks us for weight, which is mass times the acceleration due to gravity. And we also know that work equals mass times the acceleration due to gravity times height, or W equals mgh. If we switch the work equation to solve for mg, we get that mg equals work over height. And since mg equals weight, we find that weight equals work over height.
Now, since the problem has given us work and height, we can just fill those numbers into our weight equation and we'll get the answer.
The work done by Bumpkin Bill equals 9,600 joules. The safe is raised to a height of 16 meters. Filling into our equation, weight equals work over height. We get weight equals 9,600 joules divided by 16 meters. We know our answer will be in newtons because 1 joule is a newton meter, and a newton meter divided by a meter is a newton. So dividing that out, we find that the weight of the safe is 600 newtons.
Quitting time. Well, now that we're finished with work, let's talk about power.
Section B, power.
You know, in everyday life, when we think of power, we think in terms of strength, might, morphins, and rangers.
But in physics, power is the rate at which work is done. So, the less time it takes for work to be done, the more powerful something is.
So, power, capital P, equals work, W, over time, T.
The unit of power is the watt, capital W. The watt is a unit, so don't get this confused with weight, little w, or work, big W. 1 watt equals 1 joule per second. Sometimes the power can be large. In that case, it might be easier to measure it in kilowatts, small k, big W, where 1,000 watts equals 1 kilowatt.
Some of you may be more familiar with another unit of power, the horsepower.
The horsepower is represented by little h and little p, and is equal to 746 watts. But for our purposes, we're going to be working with the watt and kilowatt.
Every night when Workin' Joe gets home, he takes his tools and puts them on the shelf in his garage. His toolbox has a mass of 23 kilograms, and Working Joe raises the toolbox 1.8 meters in 1.4 seconds. How much power did Working Joe generate during that time?
First, let's start with the power equation. Power, capital P, equals work over time. The time it takes to lift the box is 1.4 seconds. Now, to complete the equation to solve for P, we have to find the work. Because the work was done vertically, our work equation is work equals mass times the acceleration due to gravity times height, or W equals mgh.
We fill in the numbers and get work equals the mass of the toolbox, 23 kilograms, times the acceleration due to gravity, 9.8 meters per second squared, times height, 1.8 meters, which is 406 joules.
Plug that back into the power equation and we get power equals work, 406 joules over time, 1.4 seconds. Doing the math, we find that Working Joe generated 290 watts of power while lifting up the toolbox.
That's enough wattage to power the entire city of Detroit for almost 20 minutes, if the city of Detroit was capable of being lit solely by the squeezable pen light.
Section C, kinetic energy.
So far we've been talking about work. Well, energy is the property that enables a particle to do work. The unit of energy is the joule, just like the unit of work. So what about kinetic energy?
Kinetic energy, represented by capital Ke, is the energy a particle has because of its motion. So if a particle has no motion, then it has no kinetic energy, and a sad, unenviable social life.
Like momentum, energy is conserved, and we can write the conservation of energy as an equation, where the change in kinetic energy equals the opposite of the change in potential energy, or delta Ke equals negative delta Pe.
If work is done on a particle, then the kinetic energy of the particle will increase. We can find the kinetic energy of a particle with the equation kinetic energy equals 1/2 of the mass times the velocity squared. So, Ke equals 1/2 mv squared.
The relationship between work done on a particle and its kinetic energy is expressed by the work kinetic energy principle, which states that the net work done equals the change in kinetic energy of a particle. That's W net equals Ke final minus Ke initial.
Let's put the work kinetic energy principle to work in a problem with the hot new sports car, the Alexandria Pharaoh XL.
The Pharaoh XL can go from 0 to 60 miles per hour in 4.0 seconds. If the Pharaoh's engine power output is 3.0 times 10 to the 5th watts, then what is the kinetic energy when it reaches 60 miles per hour?
Okay, we've got velocity, power, and time. So let's try to solve this problem. First, let's see what we can do with power and time. We've learned the equation power equals work over time. Using this equation, we can find work. Once we know what work is, we can then find the final kinetic energy, because the work kinetic energy principle states that the net work equals final kinetic energy minus initial kinetic energy.
Our first step is to isolate work in the equation P equals W over T. Doing this, we get W equals P times T. In our sports car problem, we're given that power equals 3.0 times 10 to the 5th watts, and time equals 4.0 seconds. Filling into the equation and multiplying P times T, we get that work equals 1.2 times 10 to the 6th joules, which is the amount of work done by the car.
Now that we've got the work done by the Pharaoh, we can figure out the kinetic energy of the car when it hits 60 miles per hour using the work kinetic energy principle. W net equals Ke final minus Ke initial.
W net equals Ke final minus Ke initial. We know the initial kinetic energy because the car starts at 0 miles per hour. So Ke initial is 0. So W net equals Ke final minus 0, or just Ke final. Filling in the work value we just found, we get that Ke final equals 1.2 times 10 to the 6th joules.
Notice that we didn't use the Pharaoh's velocity for any calculations. We just put in extraneous information to throw you off. Just to be intentionally evil. But in all seriousness, you'll often get problems that tell you information that you won't need to solve the problem. Now, let's review.
Work is the dot product of force and displacement. If theta is the angle between the force and displacement vectors, then work, W, equals Fx times the cosine of theta. The unit of work is the joule, which is 1 Newton meter.
When an object moves vertically, work equals mass times the acceleration due to gravity times height, or W equals mgh, and is equal to the change in gravitational potential energy of the object.
Power is the rate at which work is done. Power, P, equals work, W, over time, T. The unit of power is the watt, which is 1 joule per second.
The net work done on a particle equals the change in kinetic energy of the particle, Ke, and kinetic energy equals 1/2 of the particle's mass times its velocity squared, or Ke equals 1/2 mv squared.
And the work kinetic energy principle encompasses the relationship between work and kinetic energy, where net work equals final kinetic energy minus initial kinetic energy. And that's an overview of work and energy.
Part 2, Gravitation.
Section A, the law of universal gravitation.
Have you ever wondered about the mystery of attraction? Two people lock glances across a crowded room.
A deadly tsetse fly eyes your arm from across the park on a hot summer's day.
A restless dog eyes a fire hydrant on a crowded city street.
The planets are pulled towards the mighty sun.
But why? What exactly attracts one thing to another?
Well, the attraction between every object in the universe is due to gravitation. This attraction is described by the law of universal gravitation. The law of universal gravitation states that every object in the universe attracts every other object in the universe with a force that's proportional to the product of their masses divided by the square of the distance between them. Or, more simply, this can be written as an equation where F equals g times m1 times m2 over r squared. F equals the gravitational force, m1 is the mass of the first object, m2 is the mass of the second object, and r is the distance between the objects.
Now for the g. G is a universal constant called the gravitational constant, and by experimentation, it's been found to equal 6.67 times 10 to the negative 11th Newton meter squared per kilogram squared, when the masses are measured in kilograms and the distance in meters.
So you got that number down? Good. Let's do an example.
Say we're given that the sun's radius is 6.96 times 10 to the 8th meters. The sun's mass is 1.99 times 10 to the 30th kilograms, and the Earth's radius is 6.38 times 10 to the 6th meters. If a huge pizza pie weighs 22 newtons on Earth, how much does it weigh on the sun?
Let's figure out how to tackle this problem. We need to find the weight of the pizza pie on the sun. We know that weight equals mass times the acceleration due to gravity. Since the given weight of the pizza pie is 22 newtons on Earth, we can get the mass of the pie because we also know the acceleration due to gravity on Earth.
Next, we're going to have to figure out what the acceleration due to gravity is on the sun. But first, let's go ahead and figure out the mass of the pizza pie.
The pizza pie's weight on the Earth is 22 newtons. Weight equals mass times the acceleration due to gravity on the Earth's surface. So, 22 newtons equals mass times 9.8 meters per second squared. Solving for m, we find that the mass of the pizza pie at the Earth's surface equals 2.2 kilograms.
Okay, so we have the mass of that pizza pie. Now we've got to figure out the acceleration due to gravity on the sun. We can do that by using our fancy new force of gravitation equation. Force F equals g times m1 times m2 over r squared.
Since weight is the force of gravity on an object, we can put weight in for force in our gravitational equation. So weight equals g times m1 times m2 over r squared.
But I don't see the acceleration due to gravity in the equation. It tastes like carbon.
You don't see it now, but wait. Now look. Since weight equals mass times gravity, we can substitute mg for w. So now, what's mass 1 and mass 2? Well, mass 1 is the mass of the object on the sun, and mass 2 is the mass of the sun. Since the weight we're looking for is the weight of an object on the sun, that means this is mass 1 times gravity on the left side here. Remember, r is the sun's radius, and big G is the gravitational constant.
Now watch this. If we divide both sides by the mass of an object on the sun, those masses cancel out. That leaves us with the acceleration of gravity on the sun equals g times the mass of the sun over the sun's radius squared.
Remember, we're trying to find the acceleration of gravity on the sun so we can use it to figure out the weight of that pizza pie. We know the sun's mass is 1.99 times 10 to the 30th kilograms, and we know the sun's radius is 6.96 times 10 to the 8th meters. Since we just found the equation we need to use to find the acceleration of gravity on the sun, we're finally ready to plug in those numbers. Do it, and we get g of the sun equals 6.67 times 10 the negative 11th Newton meters squared per kilogram squared times 1.99 times 10 to the 30th kilograms over 6.96 times 10 to the 8 meters quantity squared.
Now we need to crank through this big mess of numbers and units to get our answer. To make this easier on ourselves, let's put the units aside for now while we work out the numbers. Then go back and figure out the units for our answer. Let's tackle the numerator first. Remember that when multiplying scientific notation, we multiply the numbers out in front, then add the exponents on the tens. So, 6.67 times 1.99 equals 13.27, and adding the powers of 10, we have negative 11 plus 30, which is 19. So our numerator is 13.27 times 10 to the 19th. For the denominator, we just square 6.96 times 10 to the 8th, which is 48.44 times 10 to the 16th. Dividing this into the numerator, we just divide 48.44 into 13.27, then subtract the exponents on the tens. This comes out to 0.274 times 10 to the third. Since this is not an extremely large or small number, we can take it out of scientific notation, leaving us with an answer of 274. But 274 watts? Going back to our units, we had newtons times meters squared over kilograms squared, all times kilograms, all over meters squared. To work out our units, recall that a newton is a kilogram meter over seconds squared. Substituting that for newtons, canceling out kilograms in the numerator, then canceling out meters squared in the numerator and denominator, we are left with meters per second squared. And that's the unit we use for acceleration, so we must have done something right. After all our computations, we find that the acceleration due to gravity on the Sun is 274 meters per second squared.
Wow, that's what you call some serious pull. That's 28 times the pull of the Earth. So, aside from being lonesome and the pizza being hot enough to kill you instantly, it's also fairly difficult to move on the Sun. The lesson here, don't go to the Sun. Anyway, now that we have the acceleration due to gravity on the Sun, we can figure out the way to that pizza pie on the Sun by using weight equals mg.
Since weight equals mass times the acceleration due to gravity, we can fill in the values for mass and gravity that we just figured out. So, the pizza pie's weight equals 2.2 kilograms times 274 meters per second squared, which is 603 newtons.
Not only is 603 newtons pretty heavy for a pizza, but you'd never get a chance to eat it before it would burst into flames. And let's not mention what would happen to you.
Now that we've learned about the attraction between objects in the universe, let's look at how planets and other orbiting objects check each other out.
Section B, Kepler's laws of planetary motion.
Upon careful observation of planetary motion, scientists realized that the planets have common regularities.
So Johannes Kepler, an astronomer and mathematician, stated these regularities in his laws of planetary motion.
Kepler's first law is that each planet has an elliptical orbit with the Sun at one focus.
An ellipse is a plane figure such that the sum of the distances from any point on the figure to two fixed points in the plane is constant. Each fixed point is called a focus. The longer line segment through the foci is the major axis. Half of that is called the semi-major axis. And perpendicular to the major axis, going through the ellipse's midpoint, is the minor axis. Remember this? Well, Kepler's second law states that an imaginary line that connects the Sun to any planet sweeps out equal areas in equal times.
Kepler's third law, and you'll probably use this a lot, states that the square of the planet's orbital period is proportional to the cube of its semi-major axis.
Remember, we learned about an object's period in the gravity-packed world of physics, Part 1. The period, capital T, is the time it takes for an object to complete one orbit. The period, measured in seconds, is how long it takes for a planet to complete one orbit around the Sun. Or we can use it for any object that orbits around another, like two satellites. So Kepler's third law states that the square of an object's orbit around another object equals a constant times the orbiting object's semi-major axis, cubed. We can write this as an equation where the constant has been found to be 4 pi squared over the gravitational constant times the mass of the body around which the object orbits.
For us, then, t squared equals 4 pi squared over g times m times a cubed, where t is the period of the planet, g is the gravitational constant, m is the mass about which the object orbits, and a is the orbiting object's semi-major axis, or its orbital radius.
Got that? T squared equals 4 pi squared over gm times a cubed. So let's try this baby in a problem.
Titan, a moon of Saturn, has an orbital radius around Saturn of 1.22 times 10 to the 9th meters, and Saturn has a mass of 5.6 times 10 to the 26 kilograms. So how many days does it take for Titan to complete one orbit around Saturn?
First, let's figure out what the question is asking us to find. It's asking us how many days it takes a moon of Saturn, Titan, to complete one orbit around Saturn. Well, that's the period t. Let's look at our equation. we've been given the mass of Saturn, m, and we know the gravitational constant, g, right? And the problem gives us a because that's the orbital radius of Titan, which is also the length of its semi-major axis. So now we can crank out an answer.
T squared equals 4 pi squared over gm times little a cubed. Filling in our values, we get t squared equals 4 pi, which will approximate as 3.14 squared, over the gravitational constant 6.67 times 10 to the negative 11th newtons times meters squared over kilograms squared times the mass of Saturn, 5.6 times 10 to the 26 kilograms, all times the semi-major axis, 1.22 times 10 to the 9th meters cubed. Now, let's do the numbers, then figure out the units. Starting over here and cubing 1.22 times 10 to the 9th, we get 1.82 times 10 to the 27th. Now, squaring 3.14 in the numerator and multiplying by 4, we get 39.4. Multiplying this by the number we just got on the outside, we get 71.71 times 10 to the 27th. In the denominator, 6.67 times 10 to the negative 11th times 5.6 times 10 to the 26th is 37.35 times 10 to the 15th. Dividing these two answers, we get that t squared equals 1.92 times 10 to the 12th. Okay, how about the units? Well, we have meters cubed over newtons times meters squared over kilograms squared times kilograms. Converting newtons to kilogram meters over seconds squared, we can start canceling things out. The meters all cancel out, as well as the kilograms, so we just have 1 over seconds squared in the denominator, which flips over to leave us with seconds squared as the unit for our answer. Now, we're not quite done because this is t squared, and we're looking for t. So taking the square root, we get 1.39 times 10 to the 6th seconds. So Titan's period is 1.39 times 10 to the 6th seconds.
Now, if you're not sure if you set up the equation properly, one way to check is if you look at the units. If the units cancel out and you end up with just seconds, you did it right. And remember, there's always your insert card. Isn't it great to be done with this Kepler's third law problem? Kepler would be proud.
But wait, we're not done yet. We just found out Titan's period, 1.39 times 10 to the 6 seconds. But the problem asks for us to find Titan's period in days.
Okay, we know that Titan's period is 1.39 times 10 to the 6th seconds. There are 60 seconds in 1 minute, 60 minutes in 1 hour, and 24 hours in 1 day. So, in order to convert 1.39 times 10 to the 6 seconds into days, multiply by all the ratios, and we get 16.1 days.
So it takes Titan 16.1 days to make one orbit around Saturn.
Wow, I love all this planet stuff. I'll be sure to check out the Really Big World of Astronomy Part 1 and Part 2, but only after the review.
Gravitation is the attraction between every object in the universe. The law of universal gravitation states that the attractive force between two objects is proportional to the product of the masses of the two objects over the square of the distance between the objects, or F equals G times M1 times M2 over R squared.
The g in this equation is the gravitational constant and has a value of 6.67 times 10 to the negative 11th Newton meters squared over kilograms squared.
Kepler stated 3 laws of planetary motion. The first is that every planet has an elliptical orbit with the Sun at one focus. The second is that an imaginary line that connects the Sun to any planet sweeps out equal areas in equal times. And Kepler's third law states that the square of a planet's orbital period is proportional to the cube of its semi-major axis. T squared equals 4 pi squared over gm times a cubed.
Part 3. Harmonic motion.
There are many events around us that keep repeating. The passing of seasons, the cycle of birth and death, the changing of a child star from cute to awkward and difficult to look at. And right now, we're going to learn about some other repeating events in
Section A, simple harmonic motion.
Simple harmonic motion is a basic vibratory oscillation, like when a spring vibrates or when a tree sways in the wind.
Every system in simple harmonic motion has a period, which is the time it takes for the system to complete one full cycle of vibration, or the time it takes the motion to go back and forth.
We can use a spring to understand how simple harmonic motion gets the force it needs to work. For example, when we stretch out or push in a spring, it returns to its normal length. This is called a restoring force. The more we stretch out or push in the spring, the more restoring force we've got to overcome.
This relationship is called Hooke's law. Hooke's law states that the magnitude of the restoring force is directly proportional to the displacement.
This is commonly written as an equation, F equals negative k times x, where F is the magnitude of the restoring force, x is displacement, and k is a constant, measured in newtons per meter. The value of k depends on the nature of the object and is often called the spring constant. For example, the k for a spring has a higher value if the spring is more stiff. The minus sign in the equation indicates that the restoring force is always in the opposite direction to the displacement.
Now let's get a little deeper into this spring stuff. Suppose we have a spring and we hang an object from it. Because of the weight of the object, the spring will stretch out as the weight of the object pulls it down. This distance is the displacement x. So x is both the distance the object has lowered and the distance the spring is stretched. So, if we think about this in terms of energy, the object has lost gravitational potential energy, PE, because it's been lowered, and the spring has gained energy because it's been stretched out. Just think about what would happen if we took the weight off. That spring would shoot back up.
The energy the object lost didn't magically disappear. By stretching the spring, an amount of work has been done on the spring equal to 1/2 of the spring constant, k, times the square of the displacement. So work equals 1/2 kx squared, and the lost gravitational potential energy of the object has been stored in the spring.
Now, the system of the object and spring are in equilibrium, where the force of gravity acting down on the mass, its weight, mg, is balanced by the force of the spring up, which is equal to kx.
When we stretch a spring, we do work on the spring equal to 1/2 kx squared. This work done is called elastic potential energy. So, the lost gravitational potential energy of the object winds up as elastic potential energy in the spring.
The energy of the system, the object and the spring, is the same after the spring is stretched as it was before. In other words, the energy of the system is conserved. It's just been transferred from one form to another.
Now let's change the energy of the system by raising the object just a bit so work has been done on it. When the object is let go, it begins to fall, gaining kinetic energy. The spring stretches beyond the equilibrium point and eventually stops the object from going down further. The spring then moves the object back up past the equilibrium point, and so on, until it comes back to rest at the equilibrium point. But if there's no friction, then the motion will go on forever.
The energy added to the system remains in the system. What you see is the elastic potential energy of the spring, 1/2 kx squared, transferring into kinetic energy of the object, 1/2 mv squared. That is, 1/2 kx squared equals 1/2 mv squared.
When the object is as high as it goes, its kinetic energy is 0, and its elastic potential energy is maximum.
In the middle, the equilibrium point, the displacement x is 0, and its kinetic energy is maximum.
You should also know that when we do problems with an object attached to a spring, the mass of the spring is often negligible to the mass of the object. Okay, so let's try out what we just learned.
Suppose you have a vertical spring that has a spring constant of 100 newtons per meter. Attached to it is a package of hot dogs that has a mass of 0.5 kilograms. Our question is, if you stretch out the spring 0.2 meters, then release it, what will be the velocity of the hot dog package when it returns to its previous position?
Well, when the spring is released, its elastic potential energy is converted into the kinetic energy of the package of hot dogs. When the spring returns to its original position, or the equilibrium position, all of the potential energy has turned into kinetic energy. So 1/2 mv squared equals 1/2 kx squared. Assuming that the spring's mass is negligible compared with the hot dogs, We can now solve for the velocity of the hot dogs, v.
Our equation is 1/2 mv squared equals 1/2 kx squared. The spring constant is 100 Newton meters. The mass of the hot dogs is 0.5 kilograms. X, the distance the spring was stretched, is 0.2 meters. Filling in our values, we get 1/2 times 0.5 kilograms times velocity squared equals 1/2 times 100 newtons per meter times 0.2 meters quantity squared. We can isolate v squared by dividing both sides by 1/2 times 0.5 kilograms, which cancels out on the left side, leaving us with v squared equals 8 meters squared per second squared. And taking the square root of that, we find that v equals 2.8 meters per second.
So when the spring returns to its equilibrium position, the velocity of the hot dogs is 2.8 meters per second. Pretty fast for a pack of meat.
Section B, behavior of systems undergoing simple harmonic motion.
We've talked about simple harmonic motion in order to understand Hooke's law. Now we're going to talk about the behavior of a system when it undergoes simple harmonic motion.
When a system undergoes simple harmonic motion, the period, t, of the system is the time it takes to complete one cycle.
A cycle is one complete motion of an object in simple harmonic motion. For example, one cycle is when a stretched spring completes one up and down motion. So a cycle refers to the motion itself, while the period refers to the amount of time it takes to complete one cycle.
Frequency is a quantity that we use a lot when we discuss harmonic motion. Frequency is the number of cycles per unit of time, the reciprocal of period, or 1 over the period. We represent frequency with a lowercase f. So, f equals 1 over t. And since frequency is the reciprocal of period, its unit is 1 cycle per second, which is called the hertz, capital H, little z.
And the maximum displacement of an object undergoing simple harmonic motion from its equilibrium position is called the amplitude.
So, the amplitude is the distance here, not here, or even over here, but all the way to the farthest distance from the equilibrium position in the cycle. That's the amplitude. And one entire up and down motion is called a cycle. The time it takes to complete one cycle is the period, and the frequency is just 1 over the period. That's what we know so far.
Now, if there's an object attached to the spring, then the period of the motion equals 2 times pi times the square root of the mass of the object over the spring constant, or t equals 2 pi times the square root of m over k.
Suppose this chunk of Munster cheese has a mass of 0.45 kilograms and the spring constant is 95 newtons per meter. Then what is the frequency of the motion?
We have the equation t equals 2 pi times the square root of mass over the spring constant. Frequency isn't in this equation, but we can find frequency by finding the period t, then inverting that to get frequency.
So, t equals 2 pi times the square root of m over k. M, the mass of the cheese, equals 0.45 kilograms, and K, the spring constant, equals 95 newtons per meter. So, filling in the values and working that all out, we find that T equals 0.43 seconds.
So, the period equals 0.43 seconds. Remember, frequency equals 1 over the period, or F equals 1 over T. So to find the frequency, we just have to flip this over. Plugging in our numbers, F equals 1 over 0.43 seconds. Simplifying this, we get 2.3, which is the number of cycles per second the Munster cheese makes. And remember, the unit of frequency is the hertz, which stands for cycles per second. So our final answer is 2.3 hertz. Now, let's sit back, eat our Munster cheese, and watch this next section.
Section C, the simple pendulum.
The simple pendulum. Some use the pendulum as a convenient hypnotic device.
Follow the smooth motion of the pendulum. You will give me a passing grade on my physics test. You will give me a passing grade on my physics test.
Some people just use it to set up physics problems. Either way, the simple pendulum consists of a mass that swings on a cord of negligible mass.
That means that we can ignore the chord's mass for our purposes. If the angle of the swing is not too large, then the period of the pendulum is 2 times pi times the square root of the length of the pendulum divided by the acceleration due to gravity. Let's see that equation in action and do an example.
Let's say you've timed the period of a pendulum and found it to be 4.6 seconds, and you want to know how long the chord of the pendulum is. Well, you could either measure the chord, or you could use our fancy new equation. So let's do it.
Well, we have the period, so to find length, all we've got to do is plug in our values in the equation period equals 2 times pi times the square root of length over the acceleration due to gravity. Then we'll get our answer.
That's t equals 2 pi times the square root of L divided by g. To isolate length, square both sides and we get t squared equals 4 pi squared times L over g. Solving for L equals gt squared over 4 pi squared. Filling in the acceleration due to gravity, 9.8 meters per second squared, and the period, 4.6 seconds, we get L equals 9.8 meters per second squared times 4.6 seconds squared divided by 4 pi squared. After all that, we find that the length of the pendulum is 5.3 meters.
Wow, that's one long pendulum. I wouldn't want to even be in the same town as that thing. I think it's time to review.
Simple harmonic motion is the basic vibratory motion an object undergoes when it is subjected to a restoring force that's directly proportional to its displacement from equilibrium. This type of force obeys Hooke's law, F equals negative kx, where k is the constant of proportionality particular to every object undergoing simple harmonic motion. The maximum potential energy of the system equals the system's maximum kinetic energy, or 1/2 mv squared equals 1/2 kx squared.
The period t of an object undergoing simple harmonic motion is the time it takes to complete one cycle. Frequency, f, is the inverse of period and is measured in hertz, and the amplitude is its maximum displacement. For an object oscillating on the end of its spring, its period, t, equals 2 pi times the square root of mass over k, and the period of a simple pendulum equals 2 pi times the square root of length divided by g.
Part 4. Waves. All right.
A wave is a periodic disturbance. Waves can occur when there's a disturbance in a medium, like when you drop a ball into the medium of water. Or like when you hear some cool music. The sound is carried through the medium of air.
Waves carry energy from one place to another. You'll be able to see this when we demonstrate wave motion.
Section A, wave motion.
We can demonstrate wave motion by using a rope. But warning, do not try this at home. While doing so, others could see you and brand you a rope dork. So if I'm holding a piece of rope at one end and Matt is holding it at the other end, we can make a wave when I do this.
Hey, look at the rope dorks.
Aww.
Traveling down the rope is the pulse. The top of each wave is called the peak. The bottom of each wave is called the trough. The middle section where the string was originally held is called the equilibrium position, and the distance from the top of the peak to the equilibrium position is the amplitude of the wave.
The pulse travels down the rope at a speed v. The distance from one peak to the next is the wavelength, symbolized by the Greek letter lambda, and the number of waves that pass a certain point per second is the wave's frequency.
If Matt keeps moving his hand without stopping and regularly, one pulse would follow another regularly. This is called a periodic wave. For example, sound and light waves are almost always periodic waves.
Section B, wave speed.
We can write the relationship between a wave's speed, its frequency, and its wavelength as the wave's speed equals its frequency times its wavelength. That's v equals f times lambda. The squiggly upside down y is the Greek letter lambda.
If a radio transmits at a frequency of 1.0 times 10 to the 7th hertz with a wavelength of 30.0 meters, then at what speed do the radio waves travel?
Okay, we need to find the speed. We know that speed equals frequency times wavelength. We already have frequency and wavelength, so all we have to do is fill those numbers into our equation. V speed equals f frequency times lambda wavelength.
So, the speed of those radio waves equals frequency, 1.0 times 10 to the 7th hertz times wavelength, 30.0 meters. And we find that the speed of the radio waves Work and Joe transmits is 3.0 times 10 to the 8th meters per second.
So, radio waves, a form of light, travel at the speed of light, 3.0 times 10 to the 8th meters per second. You just found out the speed of light. Now watch me as I attempt to beat light in a road race.
Section C, types of waves.
There are 3 types of waves: transverse, longitudinal, and surface.
For transverse waves, the motion of the particles of a medium is perpendicular to the motion of the wave, like the up and down motion of the particles in waves in a stretched string. The waves are traveling straight across, but the movement of the string is up and down. That's a transverse wave.
For longitudinal waves, the particles of the medium move parallel to the direction of the wave motion, like how these particles move parallel to the direction of the wave in this coil spring. The spring is moving back and forth in the same direction the waves are traveling. That's a longitudinal wave.
And water waves are an example of surface waves, where each particle of water at the surface has a circular motion, but the circle center stays in one place as the waves move across the surface. That's a surface wave.
As we know from the use of various string instruments, for transverse waves on a stretched string, the frequency depends on the tension, and low frequencies come by using heavy strings.
Through experiments, we can find that the wave speed in a stretched string equals the square root of the tension in the string over the mass per unit length of the string.
Remember, we talked about tension in ropes in the gravity-packed world of physics part 1. Well, it's the same thing for strings. Tension is the magnitude of the force the string exerts on an attached object. The unit of tension is the Newton, and it's represented by capital T. Length is represented by capital L. So we can write the formula wave speed equals the square root of tension over mass per unit length as V equals the square root of T over m divided by L. And we can remember that equation by saying Wittmüll.
Meet Cece DeShell, physics student by day, amateur speed metal guitarist by night. Cece has all the trimmings of a speed metal guitarist, but sometimes Cece needs help tuning his guitar. To hit the notes he likes, Cece needs to generate a sound wave with a speed of 350 meters per second.
If Cece's guitar string is 0.60 meters long and has a mass of 0.003 kilograms, how much tension does Cece need in his string to generate a wave speed of 350 meters per second?
Wave speed equals the square root of tension over mass divided by length. Now, all we have to do is isolate T, then fill in the numbers. Squaring both sides, we get that V squared equals T over m divided by L. T equals mv squared over L.
Filling in our values, T, the tension, equals the mass of the string, 0.003 kilograms, times the speed of the wave, 350 meters per second squared, divided by the length of the string, 0.60 meters. Working all that out, we find that the tension in the guitar string is 613 newtons, which is how tight Cece's guitar string needs to be to generate a wave speed of 350 meters per second.
A wave is a periodic disturbance. There are different parts of a wave. The bump, which is sent, is called the pulse. The top of each wave is the peak, the bottom is called the trough. Where the wave originally began is called the equilibrium position, and the top of the peak to the equilibrium position is the amplitude. The pulse travels at speed v. The distance between peaks is the wavelength lambda. The frequency f is the number of waves that pass a certain point per second, and the waves that move ceaselessly and regularly are called periodic waves.
The speed of a wave equals its frequency times its wavelength, or V equals F times lambda. And there are 3 types of waves: transverse, longitudinal, and surface waves. Transverse waves occur when the particle motion is perpendicular to the wave motion. Longitudinal waves occur when the particle motion is parallel to the wave motion. And for surface waves, the particles move in a circular motion, while the circle center stays in one place.
And for transverse waves on a stretched string, wave speed equals the square root of the tension over the mass divided by the string length, or V equals the square root of T over M divided by L. And that's it.
Part 5. Heat.
Suppose you open a sliding door to cool down your overheated living room. What causes the temperature to change in the room? Well, hold on to your hats. We'll find out the answers to these questions and more.
Section A, heat transfer.
Heat is the energy that is transferred from one object to another, or from a group of objects to another, due to a difference in temperature. And the temperature of a substance is the measure of average kinetic energy of the motion of its particles.
Heat is represented by capital Q, and the unit of heat is the joule, capital J, just like the unit of work and energy. And that's because heat is merely another form of energy.
Now, each kind of material has a different ability or capacity to hold heat. The more heat a substance can hold, the more difficult it is to make that substance change its temperature.
For example, it takes less heat to change the temperature of 1 kilogram of aluminum than to change 1 kilogram of water by the same amount. So water has a higher capacity to hold heat than aluminum.
How much heat it takes to change the temperature of 1 kilogram of a substance by 1 degree Celsius is called its specific heat capacity. It's represented by a little c and is measured in joules per kilogram degrees Celsius. Some of you might work with calories instead of joules. The calorie is the amount of heat it takes to raise 1 gram of water by 1 degree Celsius. This is the specific heat capacity for water, but we're going to be working with joules per kilogram times degrees Celsius.
Now, speaking of water, here's water's specific heat capacity in joules per kilogram degree Celsius. It takes 4,186 joules of heat to raise the temperature of 1 kilogram of water by 1 degree Celsius. Some of you might have to memorize this because you'll work with it a lot. So for water, C equals 4,186 joules per kilogram degree Celsius.
We can also find out how much heat it takes to raise a kilogram of any substance from one temperature to another. To do that, the equation we use is heat, Q, equals the mass of the substance, M, times its specific heat capacity, C, times the change in temperature, delta T. So, Q equals MC times delta T. Let's do an example.
Suppose we have 1 kilogram of water at 50 degrees Celsius. How much heat will it take to raise the temperature to 55 degrees Celsius?
Okay, we have everything we need to solve the equation Q equals mc times delta T. Mass, M, is given as 1 kilogram. The specific heat capacity of water, C, we've memorized, right? That's 4,186 joules per kilogram degree Celsius. And the change in temperature, delta T, is the final temperature, 55 degrees Celsius, minus the initial temperature, 50 degrees Celsius, which is 5 degrees Celsius. Just plug in those numbers and crank out an answer.
So, Q equals 1 kilogram times 4,186 joules per kilogram degrees Celsius times 5 degrees Celsius, which equals 20,930 joules. That's the amount of heat it will take to raise the temperature of 1 kilogram of water from 50 to 55 degrees Celsius.
Now, when we're dealing with big numbers like that, sometimes it's easier to work with kilojoules, kJ, instead of plain old joules. 1,000 joules equals 1 kilojoule. So, to convert our answer of 20,930 joules into kilojoules, we just multiply by the ratio of 1 kilojoule to 1,000 joules, and we get that 20,930 joules equals 20.93 kilojoules.
So to raise the temperature of 1 kilogram of water from 50 degrees Celsius to 55 degrees Celsius, it takes 20,930 joules, or 20.93 kilojoules.
Now that we've learned how to obtain the amount of heat transferred, let's learn about heat in an isolated system. An isolated system is any set of objects that we want to look at.
Conservation of energy also applies when we use heat, so long as no heat comes from nor goes to anywhere else. So, since energy is conserved,
The total system neither gains nor loses any heat, but individual objects within the system may gain or lose heat. For example, it takes energy to melt ice, whereas freezing water gives up energy.
For example, suppose we have a very hot piece of aluminum at 200 degrees Celsius with a mass of 2 kilograms, and suppose we drop the hot aluminum into a 10 kilogram tank of water.
Say the 10 kilogram tank has an initial temperature of 20 degrees Celsius. If the specific heat capacity of aluminum is 900 joules per kilogram degrees Celsius, then what will be the final temperature of the aluminum and the water after we drop the aluminum in the tank?
In order to tackle this problem, let's think about what's happening to the total system. Assuming that no heat is transferred anywhere else, the temperature of the aluminum will eventually be the same as the temperature of the water. So the water will gain heat, and the aluminum will lose heat. Since heat gained equals heat lost, the resulting final temperature of the aluminum and the water is called the equilibrium temperature. We'll call it T sub E.
In order for the system to reach an equilibrium temperature, the temperature of the water will have to rise, and the temperature of the aluminum must drop. So, the final temperature of both the aluminum and the water, T sub E, will be higher than the initial temperature of the water, 20 degrees, and lower than the initial temperature of the aluminum, 200 degrees Celsius. And the change in temperature for the water, delta T for the water, will be T sub E minus 20 degrees. And the delta T for the aluminum will be 200 degrees Celsius minus T sub E.
Because the heat, Q, gained by the water equals the heat, Q, lost by the aluminum, we can find out the final temperature for both substances by equating the heat gained to the heat lost, and then solving for the final temperature. So first, let's calculate the heat gained by the water by using our formula Q equals mc times delta T. Remember, Q represents heat.
So Q, gained by the water, equals the mass, m, of the water times the specific heat capacity of water, C, times the change in temperature, delta T for the water.
We were given the mass of the water, 10 kilograms, and of course the specific heat capacity of water is 4,186 joules per kilogram degrees Celsius. And we figured out earlier that delta T is the equilibrium of temperature, T sub E, minus 20 degrees Celsius.
Filling those numbers into our equation, we find that the heat gained by the water is 10 kilograms times 4,186 joules per kilogram degrees Celsius times the equilibrium temperature, T sub E, minus 20 degrees Celsius, which is the initial temperature of the water. Now, just hold on to this equation for a second and we'll get back to it.
Now we've got to figure out the heat lost by the aluminum. Now I know what you're thinking. Your brain is fried. I sympathize. This is hard stuff and it involves heat. But hang on just a little bit longer while we figure out the amount of heat lost by the aluminum. Once we have that, then we'll be in business. We do this the same way we just did for the water.
So we go back to our heat equation, Q equals mc delta T. The heat, Q, lost by the aluminum equals the mass of the aluminum, m, times aluminum specific heat capacity, C, times the change in temperature, delta T for the aluminum.
We were given the mass of the aluminum as 2 kilograms and aluminum specific heat capacity as 900 joules per kilogram degrees Celsius. We know from earlier that the change in temperature, delta T, is 200 degrees Celsius, the initial temperature of the aluminum minus the equilibrium temperature, T sub E. Now we can fill in our numbers. The heat lost by the aluminum equals 2 kilograms times 900 joules per kilogram degrees Celsius times 200 degrees Celsius minus T sub E. Now hang on to this one a sec while we compare notes.
Now, since heat gained equals heat lost, we can equate heat gained by the water with the heat lost by the aluminum to find the equilibrium temperature. So let's go ahead and equate these puppies.
The heat, Q, gained by the water equals the heat, Q, lost by the aluminum. Using the equations we just set up, we get that 10 kilograms times 4,186 joules per kilogram degrees Celsius times T sub E minus 20 degrees Celsius equals 2 kilograms times 900 joules per kilogram degrees Celsius times 200 degrees Celsius minus T sub E. Now, we can find out the equilibrium temperature with a little algebra by solving for T sub E.
Multiplying out the left and the right sides of the equation, we find that 41,860 joules per degree Celsius times T sub E minus 837,200 joules equals 360,000 joules minus 1,800 joules per degree Celsius times T sub E. Isolating T sub E on the left side, we get that 43,660 joules per degree Celsius times T sub E equals 1,197,200 joules.
Dividing this out, we find that the equilibrium temperature equals 27.4 degrees Celsius. So the aluminum and water reach the same temperature at 27.4 degrees Celsius. And we can check that our answer is reasonable by noting that our answer is between the initial temperatures of the water and the aluminum.
Wow, look at how the water heated up and the aluminum cooled down. It's just like they say, in the state of equilibrium, all substances are created equal. Now, let's review.
Heat is the energy that's transferred from one object to another due to a difference in temperature and is measured in joules. The specific heat capacity of a substance is how much heat it takes to change 1 kilogram of it by 1 degree Celsius.
Heat, added or removed, equals the mass of a substance times its specific heat capacity times the change in temperature, or Q equals mc delta T. And in an isolated system, the heat lost by one part of the system is equal to the heat gained by the rest of the system, and the resulting temperature is the equilibrium temperature. So just cool down, because we're done with review.
Section B, changes of state.
When we talk about changes of state, we're not talking about changing from a New York state of mind
Hey, there's the Statue of Liberty.
to an Oklahoma state of mind.
Hey, there's wind sweeping down the plain.
No, we're talking about changes of the states of matter, solids, liquids, and gases. For example, water's solid form is ice. We can build sculptures with it or create refreshing summer drinks with it. We call its liquid form water. We can drink it, bathe in it, and ride on it in expensive amusement parks. And finally, steam is its gaseous state. We can power trains with it, iron clothes with it, and be badly burned by it.
So when a substance changes from one state of matter to another, like melting from a solid into a liquid or boiling from a liquid into a gas, we call that a phase change. Also, note that a substance's specific heat capacity will change depending on what state of matter it's in.
Now, even though an object, like this kebab, usually experiences a rise in temperature when heat is transferred to it, during a phase change, the object's temperature remains constant until the phase change is complete.
For example, 0 degrees Celsius is the melting point of water. So if you have ice at -10 degrees Celsius and you add heat to it, then at 0 degrees Celsius the ice melts and the liquid water forms. At this phase changing point, 0 degrees Celsius, the water is in a state of equilibrium where solid ice and liquid water both are at the same temperature. They both remain at this constant temperature until the ice has completely melted into water. So if you have only liquid water with no ice, then you know the water is at a temperature greater than 0 degrees Celsius.
Now that we know what a phase change is, it's time to learn another cool idea. The heat needed to change a phase of a substance is the mass of the substance times its latent heat. The latent heat of a substance is the amount of heat needed to turn 1 kilogram of the substance from one phase to another. A substance's latent heat varies according to what phase change the substance is undergoing. Oh, I gotta get to my talent lesson.
Latent heat is symbolized by capital L, and its unit is joules per kilogram. So when a substance undergoes a phase change, heat equals mass times its latent heat, or Q equals mL.
Now in life, different phase changes have different names. The terrible twos, puberty, the golden years. Don't worry, in physics, you've only got to learn two. Looky here.
When a solid changes into a liquid or vice versa, the latent heat is called the heat of fusion of the substance, and that's represented by L sub F. When a liquid changes into a gas or vice versa, the latent heat is called the heat of vaporization, or L sub V.
With our two heat equations, heat, Q, equals mc delta T, and Q equals mass times L, we can figure out how many joules it takes for a substance to undergo a phase change. So let's do an example.
While you've been doing physics, I've watched 5 monster movies and an obscure international sporting event. Oddly enough, one of those monster movies involved a substance undergoing a phase change. In Werewolf Surfer High, a beachfront high school is terrorized by a surfing werewolf. At movie's end, a group of students rounds up 5 kilograms of silverware to melt into silver bullets so they can stop the werewolf. Only the student in charge leaves the lab to go surfing, and the silverware gets overheated and turns into a gas. The question is, how many joules does it take to turn the 5 kilograms of silver place settings from a solid at 20 degrees Celsius into a gas at 2300 degrees Celsius?
Hey, what are we gonna do about the werewolf?
Why would a werewolf come to Hawaii?
Yeah, I don't even know. I heard this happened last summer, and it was just old Mr. Johnson.
Guys, what are we gonna do about the werewolf?
Hey, you know what? Who cares? Let's surf!
We're going to need a lot of information on silver to do this problem, including its melting and boiling points, heat of fusion and vaporization, and its specific heat capacity.
First, we're given that the melting point of silver, when solid silver turns into a liquid, is 962 degrees Celsius. The boiling point of silver, when liquid silver turns into gas, is 2,212 degrees Celsius.
Silver's heat of fusion is 88 kilojoules per kilogram. Its heat of vaporization is 2,335 kilojoules per kilogram.
And lastly, silver's specific heat capacity as a solid is 0.235 kilojoules per kilogram degrees Celsius. As a liquid, it's 0.278 kilojoules per kilogram degrees Celsius. And as a gas, silver's specific heat capacity is 0.193 kilojoules per kilogram degrees Celsius.
Before we start doing anything with those numbers, let's make a graph to get a better picture of what happens when 5 kilograms of silver at 20 degrees Celsius is heated until it becomes a gas at 2300 degrees Celsius.
Let's label the x-axis heat in joules and the y-axis temperature in degrees Celsius. As heat is added, the temperature rises to 962 degrees Celsius. We'll call that stage 1. Since that's the melting point of silver, then silver undergoes a phase change and the graph plateaus. The temperature stays the same because during a phase change, heat stops raising the temperature and works instead on changing the phase from solid to liquid.
So at 962 degrees Celsius, we find both solid silver and liquid silver. This is in stage 2. In stage 3, the temperature begins to rise and the silver is only in liquid form.
Then, at 2,212 degrees Celsius, the graph plateaus again because the temperature is at the boiling point of silver. This is stage 4, so the silver undergoes a phase change where the temperature stays the same and we find a mixture of liquid and gas. Then at stage 5, the temperature rises again and we just find a gaseous silver. So by the time it hits 2300 degrees Celsius, silver is a gas.
We can calculate how many joules it takes to heat 5 kilograms of silver at 20 degrees Celsius to 2300 degrees Celsius by calculating the heat needed for each stage, then adding up our results at the end. So let's start with stage 1.
To find the amount of heat in stage 1, we need to see how much heat it takes to change the temperature of that silverware from 20 degrees Celsius to 962 degrees Celsius, the melting point of silver. To do this, we use the equation heat, Q, equals the mass of silver, M, times its specific heat capacity, times the change in temperature, delta T. We use this equation because stage 1 is where there is only solid silver, with no phase changing occurring.
So we have that Q equals mc times delta T, and guess what? We have all the information we need to fill in the equation. The silver's mass is 5 kilograms. Its specific heat capacity as a solid is 0.235 kilojoules per kilogram degrees Celsius, and the change in temperature is the final temperature minus the initial temperature. That's 962 degrees Celsius minus 20 degrees Celsius, which is 942 degrees Celsius.
Filling in, we see that 5 kilograms times 0.235 kilojoules per kilogram degrees Celsius times 942 degrees Celsius equals 1,107 kilojoules. Notice how all the units cancel and we're left with just kilojoules. So, it takes 1,107 kilojoules of heat to complete stage 1 and raise the silver's temperature from 20 degrees Celsius to 962 degrees Celsius.
In stage 2, we need to change the phase of the silver from solid to liquid. So we have to use a different equation than what we used for stage 1 because a phase change occurs. We use the equation where heat, Q, equals mass, M, times latent heat, L. It's the latent heat that tips us off that this is the right equation, because latent heat is the heat necessary for a phase change.
Since this is the stage where we find solid silver and liquid silver together, we have to use the heat of fusion, L sub F. Remember, the heat of fusion is what we use when the substance is changing from solid to liquid. So, Q equals little m times L sub F. We were given mass and the latent heat of fusion for silver, so let's fill in what we've got. Q equals 5 kilograms times 88 kilojoules per kilogram, which is 440 kilojoules. That's how much heat it takes to complete stage 2.
In stage 3, silver is a liquid, so the specific heat capacity is different, and the temperature rises from silver's melting point, 962 degrees Celsius, to silver's boiling point, 2,212 degrees Celsius. This time, we use the equation Q equals mc times delta T, because there's no phase change and no latent heat hanging around. We know the mass is 5 kilograms and silver's specific heat capacity as a liquid is 0.278 kilojoules per kilogram degrees Celsius.
So, we plug those into our equation and we get Q equals 5 kilograms times 0.278 kilojoules per kilogram degrees Celsius times the change in temperature, 2,212 degrees Celsius minus 962 degrees Celsius. Multiplying all that out, Q equals 1,738 kilojoules, which is the amount of heat it takes to complete stage 3 and raise 5 kilograms of silver from its melting point to its boiling point.
In stage 4, we have both silver liquid and silver gas. In order to change the phase in stage 4, we go back to our equation Q equals m times L sub V. So the amount of heat equals mass times the latent heat of vaporization for silver, or 5 kilograms times 2,335 kilojoules per kilogram. There's that latent heat again. Remember, phase change, latent heat equation. Now we can plug in what we've got and crank out an answer.
We interrupt this example for an important phase-changing announcement. Remember, since we're dealing with a phase change from liquid to gas, we use the latent heat of vaporization, not the latent heat of fusion, which we use when we change from solid to liquid. They're not the same thing. Now, back to our example already in progress.
We have Q equals m times L sub V. Q equals 5 kilograms times 2,335 kilojoules per kilogram, which is 11,675 kilojoules. So that's the heat required for stage 4, where the liquid silver changes completely to a gas.
In this last stage, silver is in a gaseous state. The temperature of the silver rises from its boiling point, 2,212 degrees Celsius, to 2,300 degrees Celsius, the temperature given in the problem. To find out how many joules of heat it takes to complete stage 5, because there's no phase change nor latent heat, we go to our equation Q equals mc times delta T.
Now we just fill in our numbers. Q equals 5 kilograms times the specific heat capacity of silver gas, 0.193 kilojoules per kilogram degrees Celsius times 2,300 degrees Celsius, minus 2,212 degrees Celsius, and we get 85 kilojoules, which is the amount of heat it takes to complete stage 5, and heat the gaseous silver from 2,212 degrees Celsius to 2,300 degrees Celsius.
Now that we have the amount of heat it takes to complete all the stages, we can figure out the total amount of heat it takes to heat 5 kilograms of silverware from a solid at 20 degrees Celsius to a gas at 2,300 degrees Celsius. We do this by adding together the amount of heat we found in each of the 5 stages, which looks a little something like this.
Stage 1, 1,107 kilojoules. Stage 2, 440 kilojoules. Stage 3, 1,738 kilojoules. Stage 4, 11,675 kilojoules. Stage 5, 85 kilojoules. Now add these up and we get that it takes 15,045 kilojoules of heat for silver to go from stage 1, a solid at 20 degrees Celsius, to stage 5, a gas at 2,300 degrees Celsius.
Well, there you have it. Now that that's done, I'm going to watch the rest of my movie while you learn how heat is transferred.
I can't believe this is happening. This could be the last day of our lives.
Yeah, this has been one crazy summer.
Hi, guys. Oh, hey, it turns out that he wasn't a werewolf at all. He was just going through a phase change. We call it acne.
Cool, let's serve.
Okay.
Section C, conduction, convection, and radiation.
Heat is transferred 3 ways: conduction, convection, and radiation. If we stand near a campfire, we can show you examples of all 3 means of heat transfer.
Suppose you stick a metal fireplace poker directly into the fire and you sit there, holding on to the other end. Well, soon you'll be feeling pain in your hand because the metal will have heated up. This is because of conduction. Conduction is heat transfer via the collision of molecules.
When the end of the poker is in the fire, it gets heated, and the molecules at the end acquire more and more kinetic energy. Then, the molecules move faster and faster by vibrating around their equilibrium positions. So, while they're vibrating, they bump into their neighbor molecules, and that gets the neighbors excited.
Then, those neighbors bump into their neighbors, and so on and so on. After a while, the molecules at the end that you're holding finally get the energy, and they start to vibrate and become hot. And then, heat is transferred to your hand, and that's where the pain comes in.
That was conduction. Now we're going to talk about convection. Convection is the transfer of heat due to the mass movement of heated molecules. An example of this is when you hold your hands over a fire and your hands warm up.
Your hands start to warm up because the air directly above the fire heats up, expands, and then rises. The air then flows by your hands, and as it does, the air warms your hands.
Now, let's suppose you're sitting next to the fire, but not in it. So you don't experience conduction or burning. And you're not above it, so you don't experience convection. You're just sitting there, feeling the heat. That's because you're absorbing radiation.
The fire, like the sun, is emitting light, both visible and invisible. Some of the invisible light is heat in the form of infrared radiation. This is how the sun heats us, and how the fire heats you when you're sitting near it, but not in it or above it.
So, the next time you're with a group of friends roasting marshmallows by the fire, you can tell everyone how they're being affected by radiation.
Okay, now that we know how heat is transferred, let's look at how heat and work go together.
Section D, heat and work.
When we talked about work before, we talked about the work done by large objects. Now, we're going to talk about the work done by gases, like the internal combustion engine, where the expanding gas from burning gasoline pushes a piston.
Let's suppose we have some Einsteinium gas, and suppose that it's in a container. Now suppose that the top of the container is movable. In fact, it's a piston, so it can move up and down easily. When the piston goes up and down, the volume of the gas changes. The piston goes up because the Einsteinium gas is doing work on it.
The gas does work by applying pressure, which is force per unit area. So if the gas gets heated and expands, it will put pressure on the piston until it reaches the volume where it wants to be.
So the pressure does work on the piston, increasing the volume and causing the piston to move, thereby doing work. Believe it or not, there's a cool equation that puts this relationship in a form we can put to good use. Here it is. The change in work, delta W, equals the pressure of the gas, little p, times the change in volume, delta V. So, delta W equals little p, delta V.
If work is measured in joules, then the unit of pressure is the Pascal, capital P, little a, which is 1 Newton per meter squared, and volume is measured in meters cubed. But because the numbers we work with are so large, it's probably easier to measure work in kilojoules and pressure in kilopascals.
So, if we have steam kept at a constant pressure of 120 kilopascals, The work done by the gas is 240 kilojoules, and its initial volume was 1.03 meters cubed, then what's the final volume of the steam?
Okay, we know that the change in work equals pressure times the change in volume. Delta W equals P times delta V. We've already got work, pressure, and the initial volume, so we can now solve for the final volume.
Again, our formula for work is delta W equals P times delta V. Delta V equals the final volume minus the initial volume. So, delta W equals P times the quantity V sub F minus V sub I. Isolating V sub F, we get V sub F equals delta W over P plus V sub I. Filling in what we've been given, V sub F, the amount of work done by the steam, equals 240 kilojoules, divided by the constant pressure of the steam, 120 kilopascals, plus the initial volume of the steam, 1.03 meters cubed. Work that out, and we find that the final volume of the steam is 3.03 meters cubed. See how that worked? To do its 240 kilojoules worth of work on the piston, the steam expanded from a volume of 1.03 meters cubed to a volume of 3.03 meters cubed.
The temperature of a substance stays the same during a phase change. The latent heat of a substance is the amount of heat needed to turn 1 kilogram of it from one phase to another. And heat equals mass times the substance's latent heat, or Q equals ml. When a solid turns into a liquid, that's called the heat of fusion. And from a liquid into a gas, that's the heat of vaporization of a substance.
Heat is transferred by conduction, convection, and radiation. Conduction is heat transfer via the collision of molecules. Convection is the transfer of heat due to the movement of a heated substance. And radiation is the transfer of energy through the space between those molecules.
And the change in work done by gases is directly proportional to the pressure and the change in volume of the gas, or delta W equals P delta V. And that's it.
Part 6, Thermodynamics.
Up to now, we've been talking about heat. Well, this is where it all pays off. Thermodynamics is the branch of physics that deals with the transformation of heat into mechanical energy. And it's that mechanical energy that gets us going.
We're going to go over the first law of thermodynamics, the second law of thermodynamics, heat engines, and entropy. So let's get rolling.
Section A, the first law of thermodynamics.
When we talk about thermodynamics, we need to make it clear what the difference is between heat and work. Heat is the transfer of energy due to the change in temperature, and work is the transfer of energy that is not due to a change in temperature.
Both the heat and work affect the internal energy of the system. The internal energy, logically represented by a capital U, is the total energy of the molecules of the system.
So when a substance undergoes a phase change, internal energy changes, but with no change in temperature.
And if the system does work, this lowers the internal energy of the system because that energy is going somewhere else. Like when you lift up something heavy, you transform energy. And it works the other way too. If heat is added to the system, its internal energy increases. This relationship is the first law of thermodynamics.
The first law of thermodynamics states that the change in the internal energy of a system, delta U, equals the heat, Q, added to the system minus the work, W, done by the system. So delta U equals Q minus W. Look how this works.
If heat is removed from the system, Q, the heat added, is negative because we're taking heat away or adding a negative amount of heat. Therefore, the internal energy of the system decreases. Now, if work is done to the system, then W is negative, because the system is not doing work, it's taking work in. Therefore, the internal energy increases. Now, you can see that the first law of thermodynamics is just a generalized statement of the law of the conservation of energy, recognizing that heat is just another form of energy.
So, heat and work have to do with energy going in and out of the system. The change in the internal energy of the system is how the internal energy reacts to this transfer.
We can look at a few different situations to see how the first law of thermodynamics can be used. First, let's look at a gas where the volume is kept constant. This is called an isovolumetric process.
So, if the volume of the gas is kept constant, then the change in the volume, delta V, equals 0, because delta V equals V final minus V initial. So, if there's no change, then V final equals V initial, and the difference is 0, so delta V equals 0.
And remember when we talked about gases doing work, we learned that the change in work, delta W, equals pressure, P, times the change in volume, delta V. So, since we already found out that delta V equals 0, then the change in work done by a gas at a constant volume also equals 0, because delta W equals P times 0, which equals 0.
So, for an isovolumetric process, the change in work equals 0, so no work is done by the system or to the system. Not much of a process, is it?
Now, to figure out how an isovolumetric process affects our equation for the first law of thermodynamics, delta U equals Q minus W, we just fill in that work equals 0, and we get that delta U equals Q. So, for an isovolumetric process, the increase in the internal energy of the system equals the heat added to the system.
So, that's an isovolumetric process. Now, suppose we have a system where the pressure is constant, but the volume can change. This is called an isobaric process.
So, if delta U, the change in the internal energy of the system, equals Q, heat, minus W, work, and W equals P times delta V, then substituting P delta V in for W, we get that delta U equals Q minus P times delta V. This is the equation we would use to find the change in internal energy for an isobaric process.
The third process we're going to learn about, which involves the first law of thermodynamics, is an adiabatic process. This is when we have a system where no heat is added.
Delta U, the change in internal energy, equals Q, heat, minus W, work. If no heat is added in an adiabatic process, the heat, Q, equals 0. And delta U equals 0 minus W, or delta U equals negative W. So for an adiabatic process, the increase in the internal energy of the system equals the negative of the work done by or to the system.
All right, enough of the equation talk. Let's do a problem.
Suppose we have 1.0 kilograms of liquid water at 100 degrees Celsius, occupying 0.001 cubic meters, and subject to a pressure of 1.013 times 10 to the 5th pascals. When the water is boiled, it becomes steam at 100 degrees Celsius, with the steam occupying a volume of 1.7 cubic meters. For our problem, first, figure out what kind of process this is. Then, if we're given that the latent heat of vaporization of water is 2.26 times 10 to the 6 joules per kilogram, figure out what the change in the water's internal energy is.
Before we tackle this problem, let's sort out all the information that the problem has dumped on us. We have the mass, m, of 1.0 kilograms. We have temperature, T, of 100 degrees Celsius. The initial volume of the water, V sub I, is 0.001 meters cubed. Pressure P is 1.013 times 10 to the 5th pascals. The final volume of the steam, V sub F, is 1.7 cubic meters, and we have water's latent heat of vaporization as 2.26 times 10 to the 6th joules per kilogram.
Wow, that's a lot of information. Now that we have it all down, let's first figure out what kind of process this is. Remember, when we're dealing with the first law of thermodynamics, we've got 3 types of processes to choose from: isovolumetric, isobaric, and adiabatic. Well, for starters, the volume of the water changes, so it can't be an isovolumetric process because that's the process where the volume is constant. Also, the water changes from a liquid stage to a gas stage, and to undergo a phase change, we must add heat. So this process can't be adiabatic because that's the process where no heat is added. But the pressure in our problem is constant, so it must be an isobaric process.
The problem is asking us to find delta U, the change in internal energy of the water. And since we weren't given work, we can use the equation that we derived for delta U in an isobaric process. That's delta U equals Q minus pressure, P, times the change in volume, delta V.
Let's look at what we were given and see if we have everything we need to plug in those numbers and crank out an answer.
We have pressure P and the initial and final volumes, so we can find the change in volume, delta V. What we don't have is Q, the amount of heat added.
To find Q, we have to go back to what we learned about phase changes. In our problem, liquid water boils and turns into a gas, so it goes from the liquid stage into the gas stage. And when a substance goes from liquid to gas, we find the amount of heat added to the system by multiplying mass times the latent heat of vaporization, or Q equals M times L sub V. Remember that when we talked about phase changes?
We were given the water's mass of 1.0 kilograms and water's latent heat of vaporization of 2.26 times 10 to the 6th joules per kilogram. So now we can solve for the amount of heat added. Q equals M times L sub V. So, filling in the numbers, Q equals 1.0 kilograms times 2.26 times 10 to the 6th joules per kilogram, or Q equals 2.26 times 10 to the 6th joules.
Now that we've found the amount of heat added in order to turn the water from a liquid to a gas, we can go back to our equation for finding the change in the internal energy of an isobaric process. Delta U equals Q minus P delta V. Now we've got everything we need to fill in our numbers and find the change in the water's internal energy.
Delta U equals Q minus P delta V. Remember, delta V equals V final minus V initial. So, delta U equals Q minus P times V sub F minus V sub I. Q, the amount of heat added to the water, is 2.26 times 10 to the 6th joules. P, the pressure the water is subjected to, is 1.013 times 10 to the 5th pascals. V sub I, the initial volume of the water in its liquid state, is 0.001 meters cubed. And V sub F, the final volume of the water in its gaseous state, is 1.7 meters cubed.
Filling in our numbers, we get that delta U equals 2.26 times 10 to the 6th joules minus 1.013 times 10 to the 5th pascals times 1.7 meters cubed minus 0.001 meters cubed. Working all this out, we get 2.1 times 10 to the 6th joules. So, the change in internal energy when 0.001 cubic meters of water is changed to 1.7 cubic meters of steam is 2.1 times 10 to the 6th joules.
So, we found out the change in internal energy. You might be wondering why we were given the temperature if we didn't use it in our calculations. You might be suspicious, certain it was thrown in there just to mess with your head. To send you in the wrong direction, never to return. Well, it was actually important to know that the water was at 100 degrees Celsius, its boiling point, because that told us that it was going through a phase change. And now it's time to move on to
Section B, the second law of thermodynamics.
When we're working with the second law of thermodynamics, there are many types of processes that a system can go through. These can be divided into two groups, reversible and irreversible processes. A reversible process is one that, after it's finished, can go backwards and end up where it started. An irreversible process, on the other hand, is a process that can't go back and restore itself. All processes that occur in nature are irreversible. For example, if in a fit of rage you drop your mom's favorite vase on the floor, it'll shatter into a million pieces. Now suppose those pieces suddenly gathered themselves up and flew back into their original form. You'd probably think that you were going crazy.
For your mom's sake, it might be nice if breaking the vase was a reversible process, but it's not. It's irreversible.
Another example of an irreversible process is if we put a hot object, like this famous athlete, into direct contact with a cold object, like this frigid metal rod. Heat energy flows from the hotter object to the colder one.
The second law of thermodynamics says that heat flows naturally from a hot object to a colder one. Heat will not flow spontaneously from a cold object to a hot object.
We'll be returning to the second law of thermodynamics because there are actually many ways of stating this law and it has many implications. An important implication and application of this law is the heat engine. So let's go there.
Section C, heat engines.
In the modern world, we're obsessed with energy. We need energy to power everything from our televisions to our blenders to our intricate mind control devices. That's why we're always looking for ways to obtain more and more electrical and mechanical energy. A heat engine is a device that turns heat energy into electrical energy or mechanical energy.
Another way to look at this is to say that a heat engine turns heat energy into work. These are extremely important devices, such as car engines and steam engines. And what would we do without our cars? Would we actually eat inside a fast food restaurant? Ugh.
Let's look at how the heat engine works. There are two items required by a heat engine. First, a source of heat at a high temperature. Second, a body that's at a lower temperature, which serves as a repository or sink for the heat.
Imagine a source of heat that's so large that we can keep taking heat from it without lowering its temperature. This is called a hot reservoir. And if we can keep adding heat to the low temperature source without raising its temperature, then that's called a cold reservoir.
We'll call the temperature of the hot reservoir T sub H, and we'll call the temperature of the cold reservoir T sub C. The heat engine takes heat, Q sub H, from the hot reservoir and turns some of that heat into work, W. Then it dumps the leftover heat, Q sub C, which is now at a cooler temperature, T sub C, into the cold reservoir. So the engine is able to do work using the higher temperature, Q sub H.
Since part of the heat from the hot reservoir, Q sub H, became work, W, and the rest was deposited into the cold reservoir as Q sub C, we can say that Q sub H, the heat taken from the hot reservoir, equals W, work, plus Q sub C, the leftover heat dumped into the cold reservoir. Or if we isolate W, work equals Q sub H minus Q sub C.
We can evaluate the efficiency, E, of a heat engine by dividing the work output by the heat that's put in, Q sub H. That's E equals W over Q sub H. And if we substitute the equation for work we just found, Q sub H minus Q sub C, into the equation for efficiency, we get that E equals Q sub H minus Q sub C all over Q sub H. That simplifies to E equals 1 minus Q sub C over Q sub H.
Now that we've got the equation for efficiency, 1 minus Q sub C over Q sub H, let's do a problem.
Let's say we've built an engine that takes in 1900 joules and expels 1400 joules. What is its efficiency?
First, let's set up our information. The engine takes in 1900 joules, so Q sub H is 1900 joules. It expels 1400 joules, so Q sub C equals 1400 joules.
Remember, efficiency, E, equals 1 minus Q sub C over Q sub H. Now we can just fill in our numbers, simplify, and we get that E equals 0.26. We usually express efficiency as a percentage, so multiply that by 100, and we get that the engine has a 26% efficiency. Note that with a 26% efficiency, 74% of the heat taken from the hot reservoir does no useful work and is rejected as waste heat into the cold reservoir.
Okay, here's another problem. If an engine is 16% efficient and expels 4,200 joules, what is the work done by the engine?
Setting up the problem, we have Q sub C, 4,200 joules, and we've got the efficiency, E, is 16%, or 0.16. The problem asks us to find the amount of work done by the engine. From the equations we know, we've learned that work equals Q sub H minus Q sub C. But we don't know the amount of heat taken from the hot reservoir, so we can use our efficiency equation, E equals 1 minus Q sub C over Q sub H, to solve for Q sub H. Then plug that into our work equation.
First, let's solve for Q sub H. If we fill in what we've got for E, the efficiency, and the amount of heat dumped to the cold reservoir, Q sub C, we find that 0.16 equals 1 minus 4,200 joules over Q sub H. Next, 4,200 joules over Q sub H equals 0.84, and solving for Q sub H, we get 5,000 joules, which is the amount of heat taken from our hot reservoir. So now that we have Q sub H, we can solve for work.
Work equals Q sub H minus Q sub C. Filling in our values for Q sub H and Q sub C, we find that work equals 5,000 joules minus 4,200 joules, which is 800 joules. So, the amount of work done by the engine is 800 joules, and that's our final answer.
The problem we just did dealt with an engine that has a 16% efficiency. Some of you might wonder what would have an efficiency of 100%, with E equaling 1. Well, sorry to break it to you, but in order for E to equal 1, the temperature of the cold reservoir, T sub C, would have to be 0 degrees Kelvin, also called absolute zero. And the second law of thermodynamics forbids that, because no system continuously operating can be 100% efficient.
So using everything we've learned, we can restate the laws of thermodynamics. The first is that total energy, including heat energy, is conserved. The second law is that whenever heat is converted into work, some heat must flow into a colder reservoir. This means that no engine operating in a cycle can achieve 100% efficiency.
Or you can think of the laws of thermodynamics this way. First, you can never win because of the conservation of energy. You can't get more energy than you start off with. Second, you always lose because when heat is converted into work, some of it will flow into a cold reservoir. And third, you can't get out of the game because no system can reach absolute zero in a finite number of operations. So no engine can run at 100% efficiency. So we're just going to have to put in more energy to keep things running.
Section D, entropy.
There's one last thing that we're going to discuss about thermodynamics. It's entropy. Entropy is the measure of disorder of a system.
Suppose that you do nothing to clean up your room for a year. You never make up your bed, never put away any clothes, and you never pick up those cheese balls from the floor. Well, after a year, it would be a very scary place to live. So after a year, the entropy or disorder of your room would increase because you put no energy into keeping your room neat. Just like your room, the vase that you smashed earlier also increases its disorder. The glass was more orderly before it was broken than after. We represent the change in entropy with a delta S.
Entropy.
The fragrance of disorder.
Entropy.
It's everywhere.
And just like when a substance changes from a liquid to a gas, when it's in a gas stage, there's more disorder because gas molecules are in more disorder than the more closely held together liquid molecules. And molecules in the liquid stage are in more disorder, so they have greater entropy than molecules in the solid stage.
This can be seen if we restate the second law of thermodynamics. Remember, we first stated that the second law of thermodynamics said that heat flows naturally from a hot object to a colder object, and heat will not flow spontaneously from a cold object to a hot object. With entropy in mind, the second law of thermodynamics can be restated as natural processes tend to move toward a state of greater entropy.
In other words, everything in nature is moving towards disorder. The change in entropy can be expressed as the amount of heat added to a system divided by the temperature, or delta S equals Q over T.
But for entropy, temperature is not measured in degrees Celsius, as we've seen before. It's measured in degrees Kelvin, represented by a capital K.
The temperature in degrees Kelvin equals the temperature in degrees Celsius plus 273. So the freezing point of water, 0 degrees Celsius, equals 273 Kelvin degrees.
So, if delta S equals Q over T, then delta S is measured in joules per Kelvin. Let's try out this new knowledge in an example.
Find the change in entropy when 0.2 kilograms of lead melts at its melting point of 327 degrees Celsius. If lead has a latent heat of fusion of 2.45 times 10 to the 4th joules per kilogram.
To solve this problem, first we have to figure out how much heat it takes to change the solid lead into liquid lead. Remember your insert card and see that the equation for the amount of heat needed to go from a solid phase to a liquid phase is heat equals mass times the latent heat of fusion. Q equals m times L sub F. That's 0.2 kilograms times 2.45 times 10 to the 4th joules per kilogram, which is 4,900 joules.
Now that we know how much heat it takes to change the phase from solid to liquid, we can find the lead's change in entropy using our equation delta S equals heat, Q, over temperature, T. Remember that the temperature in this equation is in kelvins, so first we have to change 327 degrees Celsius into degrees Kelvin.
The temperature in degrees Kelvin equals the temperature in degrees Celsius plus 273. Using our information, that's 327 plus 273, which is 600 degrees Kelvin. Boy, that worked out to be a nice round number.
And filling into our equation for the change in entropy, delta S equals Q over T, we get that delta S equals 4,900 joules over 600 degrees Kelvin, which is 8.2 joules per degree Kelvin. So, that's the change in entropy when those 0.2 kilograms of lead change from a solid to a liquid.
The first law of thermodynamics states that the change in the internal energy of a system equals the heat added minus the work done by the system, or delta U equals Q minus W. An isovolumetric process is when there is a gas and the volume is kept constant, but the pressure can change. An isobaric process is when the pressure is kept constant, but the volume can change. And in an adiabatic process, no heat is added or taken from the system.
The second law of thermodynamics states that heat flows naturally from a hot object to a colder one, and heat will not flow spontaneously from a cold object to a hot one.
Heat engines turn heat energy into electrical or mechanical energy. The heat from the hot reservoir equals the work done plus the heat from the cold reservoir, and efficiency is work divided by heat. Another way of stating the second law of thermodynamics is that the efficiency of a heat engine can never equal 100%.
Entropy is the measure of disorder of a system, and the change in entropy equals heat added to a system divided by temperature, or delta S equals Q over T. And a third way to state the second law of thermodynamics is to say that the entropy of a closed system can never decrease. It will always increase as work is converted into heat. So smile, that was the last thing, and it looks like you made it.
Hey, thanks for watching the Gravity-Packed World of Physics Part 2. We know we've gone over everything from energy to entropy, but you can always rewind the tape, take a peek at the insert cards, or you could even watch the Gravity-Packed World of Physics Part 1.
After you've looked at physics, check out other tapes from the standard Deviants, like astronomy, English composition, statistics, French, and much, much more.
Now, if you have any questions,
Or you just want to call to say hello.
please give us a ring at Cerebellum.
At 1-800-238-9669.
We are Standard Deviants.
Thanks for watching.